So looks like it's 5:40, which is the time to start, so how about we start? So this talk is going to be about deep learning, and specifically about deep learning with CNTK and F#. So first, a couple of words about me very quickly. My name is Mathias Brandewinder. You can find me on Twitter and many places as @Brandewinder. I look like this guy on the right in all of these places. And the two things I'm particularly interested about recently, or actually not that recently, one of them is like functional programming, and in particular functional programming with F#. And the second side of my interests is anything which has to do with code and numbers, like numerics, optimization, and in particular machine learning. And so this is like, the talk today is like at the intersection of these two things. So the context for this talk is the following. It's starting from, I'm going to start with the two statements which I don't think are very controversial. The first one is like deep learning is a very hot topic lately. So everybody's talking about it. Not many people know what that means, but they're still excited. Deep learning is supposed to solve all our problems. It will drive cars. Everything will be better with deep learning. So that's one side. And the second side is, as a developer, most of the work I've been doing is in the space of .NET. And if you look at deep learning, like deep learning and .NET is not a hot topic. Most of the action has been happening on the Python side or other languages, but .NET has been a bit of a backwater for the topic. So this made me sad because, as I said, like on one side I'm using F#, I'm using .NET, on the other side I do machine learning. I want to have fun, I want to be a part of the hype, and so I would like to be able to do deep learning with .NET, and that was not possible for a while. Until a couple of months ago, Microsoft decided to release one of the libraries, which is called CNTK, and specifically they released with CNTK a .NET API. So this made me very happy because now suddenly I can use .NET, I can have fun with the deep learning, and so I've been playing a bit with this, and the talk today will be about the type of thing I've been doing with it, and how does deep learning with CNTK and F# and .NET in general look like. So this is what I want to talk about. In that context, so this is the plan I'm going to follow. Is like first, my assumption is like this is a developer conference, so most of you are probably not familiar with the deep learning. So I'm going to start with a shallow introduction to deep learning. I'm not going to tell you everything there is to say about it because it's too big of a topic. I'm going to try to give you an intuition of why deep learning might work, how this works, so that you have a sense for, I'm going to try to tell this with as little lies as possible, but so that you have a sense for what is it about and why you might care. From there, I'm going to go to a CNTK specifically and try to show you from what I told you before about deep learning, how does this translate into CNTK, how does the library look, and how would code look with CNTK if you go to the API out of the box. And the third part will be the out-of-the-box API is, I would say, like, not awesome, and so I've been working quite a bit on trying to make it like pleasant to use. So I'm going to show you next like what I did to make models more composable so that it was more of a pleasant experience. So let's start with the first part, which is a shallow introduction to deep learning. And I'm going to start actually with a place which has nothing to do with deep learning. And apparently it's acceptable to talk about burritos to introduce monads. So it's like, why not use something irrelevant like Donkey Kong to start talking about deep learning? So the reason I care about Donkey Kong is like, one, it's a beautiful game, but I thought it was a good example of something old, which is like 8-bit rendering. And so the specific piece I care about is like something which has nothing to do directly with deep learning. I will get there in due time. And the thing I care about is like if I look at the numbers rendered here, is like how would I go about if I wanted to print out a number in the 8-bit style? So if I look at 8-bit style, like the way this works out, is like every number is going to be rendered on a grid of 8 by 8, and roughly like each of the 64 pixels can be on or off. So either it's on and it's alive, it's light, and it's off, then nothing shows up. So if I wanted to make a system which rendered numbers in that style, one possible analogy would be the following. I can think of each pixel as a bulb, and the bulb is either like light or dark. And so the system I could build is something like this. I have an on and off switch which connects to the light, and what I want is I want the light to be on when the pixel is supposed to be on. So if I go back to my 8-bit system, what I would do is I would use something like an activation gate or something like this where I'm going to get current coming in. If I have not enough current, then the output will be 0. I have no current, the light is not on. If enough power or enough current is coming in, the output will be 1. I have enough light, and the light will go on. So in that frame, if I wanted to render, for instance, a 1, one possible strategy would be take 64 bulbs, lay them out as an 8 by 8 grid. And here I'm going to simply display like 3 of them, so 2 of them are dark and 1 of them is light, so this is what I have here. And all I would have to do would be to take like one cable and plug that one cable from I have a button on the left, which is the 1 button. So when I press it, some current is coming in, and I'm going to go and plug a cable from this into the bulbs I want to be alive. And so in that case, like when I press the button, the right pixels will be lit, and when I don't press the button, everything will be dark. So that would be like one way where I could build a simple system where I press the button, I see a 1, I depress the button, the 1 disappears. Not very complicated, a bit, so yeah, nothing, no rocket science so far. So this works. Like the one thing I don't really like about this is like there is a lot of complicated wiring going on. It's like essentially I have like 64 bulbs. I need to put the cables in the right place. This is complicated. I don't like this. So there is another strategy I could take, which is like between the switch, which is putting the current on and off. What I could do is I could use something like what you see on an amplifier, like for music, something which allows me to say, like, out of the thing you get as an input, you can tune the output from 0% to 100%. So in that case, what would happen is like if I put it on and the volume is on 0, the output will still be 0. And if I put the volume to 100% or crank it to 11, then the output will be 1. So what this would gain me is the following. Is that now, instead of having a specific set of cables plugged to the output, what I could do is like take my input button, still have like the current comes in, and now I would have 64 cables, so every single bulb will be connected to the input, but what I would have is on every single cable, I will have like a volume control button, which will go from 0 to 100%. And so what I have now is like I have a completely generic way to go from an input to any output I want with exactly the same wiring of 64 cables. All I need to do at that point is like set up how much volume should go in. So in that case, what I would do for my 3 pixels is I would have like 3 cables. One of them is going to have the volume cranked up to 100%, so that when I press the button, this pixel will be on. And the 2 others will be on 0%, so that even I press, I don't press, it doesn't matter. The output will always stay dark. One way you could think about this is like at that point is like if I laid out the weights I have and laid them, now what I have is like 8 by 8 bulbs, and I have really 8 by 8 weights or 8 by 8 volume things. And if I lay them out, it's like these really form a filter, which is, in that case, like if I wanted to represent a 1, I could see that the weights, all the weights which are at 100% are describing a filter for the thing I want to display. I could also very easily extend that principle, so now it's pretty general because I have the same type of wiring. I could use it to represent a 1, a 2, a 3, like any form of shape I want. I would just need to put a specific wiring for 1, or specific sets of weights for 1, a specific set for 2, and so on and so forth. So at that point, you might ask yourself, so this is great, but how does this relate to machine learning? And so the machine learning question will be the opposite. Like the question that looked so far was the following: if I press a 1, I want a shape of 1 to show up on the right. The machine learning question will be the opposite. Is like if I give you an image on the right side which was a 1, I would want a system which now tells me like it was a 1. And so the one way you could go about this is really say like we can reverse engineer this system. All we need to do is really to reverse the wiring completely. Instead of saying 1 is the input and this image here is the output, I could say like now my image is going to be the input. I'm going to pull the cables like not going left to right, but right to left. So I'm going to take every pixel as a signal, which could be 1 or 0. Each of them is going to go into a set of weights. And what I would want is I would take all these weights and all the input, and I would want this to give me a strong signal on 1, so that when I have an image of 1, it tells me like this is a 1. And it tells me it's not a 2 and not a 3, and so on and so forth. How would I go about this? So if I started with weights which were maybe random and maybe 0, initially my signal would be 0 everywhere. And the way I would go about this is something like this. I would pass an image of a 1. Currently, like the output would not be what I want. And I could start to poke around and change the weights. in such a way that what I really want is I want to take all these weights, which are each of them are going to get me a signal. All of them are going to be collected into the input, which goes to 1. And so what I want here is a signal which is going to be very strong when the image is a 1. The way I would do this is, in that case, I would want a weight of 0 in this one and on 0 of this one because it doesn't really matter. But like whenever the pixel is on, I would really want a strong weight on the corresponding pixel because that will give me a strong signal which is indicating you have a 1 here. So I could start to tweak the weights so that the answer I get when I get the image of a 1, the answer I will get would tell me this is a 1 and this is nothing else. This is actually, it might sound like crude or naive, but this is more or less how a machine learning algorithm works. The way the algorithm will work is that you will give it an image, an example. So the image will be, this is an image of a 1, the output should be a 1. You will compute the output by passing it through the weight up to the moment you get the output, and then you will start to tweak the weights. So in that case, you won't do it, but the algorithm will do it. And what the algorithm will try to do is like increase the output on 1 and try to decrease the output on all the other outputs. And then you would give it another example. Here is an image of a 2, and it will try to move the weights so that the answer goes up for a 2 and doesn't go up for the other ones. And you keep going and going and going. And if you're lucky, at some point, you give it an image of a 1, and it tells you it's a 1, and you give it an image of a 3, and it tells you it's a 3. So this is like, without lying too much, this is pretty much what a machine learning algorithm does. So one question I want to look at now is, suppose you had a system or an algorithm which did this, how should the weight look like until, at the point where you have a system which works? So suppose for a second that I don't want to distinguish 1, 2, 3, and all these numbers. I'm just interested in recognizing things which are 1s and things which are 2. So I would have an image here, I don't know what it is, and I'm going to pass it through 2 filters. One is supposed to detect 1s, one is supposed to detect 2. So one strategy would be like the shape of the 1 should entirely be up, or like the weights should be strong on the shape, and on the 2, the weights should also be strong on the shape of the 2. This would work, but this is not quite correct. Like the weights I would expect are the pieces I wrote or I highlighted in red on the image. And so what you see here is like they still match with the shape of the 1, but some of them are really not active. For instance, like this pixel here at the top of the 1 is not active. The reason it's not active is because like when I see this pixel on, I could conclude it's a 1, but this is also active for a 2. So when I see this signal, I can't really tell you if it's a 1 or a 2. Like I can't make a decision on this. It could be 1, it could be the other one. Similarly, if I look at this pixel here, or all these pixels at the bottom, like all these pixels belong to the image of the 1 and belong to the image of the 2. So they're not really telling me anything about is this a 1 or is this a 2. If I see this, it's like 50-50, I don't know. So in that case, is like what I would expect is like once the system has learned weights, the weights should be very strong in the area which is highlighted in red. And these are things which are completely specific to a 1 and not present on a 2. In other words, they are specific to 1 and they allow me to distinguish this is a 1 and this is not a 2. And vice versa for the 2 here. You might now say, like, there is another way to do this, which would be much simpler, is like, why do I care about all these weights? If you give me an image of a 1, if I know that this small pixel here is active, I definitely know it's a 1. I don't need anything else. If that's on, it's like, I don't care about the rest, it works, it's like, I know it's a 1 because it can't be a 2. Same strategy, I could say, like, if I take the 2, when this pixel is on, the only thing it could be is a 2 because that's never active for a 1. So this would work. This would be probably simpler because now I have just one weight and not 64. The drawback with this is like this is not a very robust system. Like if I have any flakiness in the cables, if the system is not strong, it's like now I'm relying on a single input to make my decision. So any error I have in the input is going to completely mess up the output. So this would not be a desirable outcome, and what I would really want is like a solution like this one, which is going to use like every piece of input which is useful to take the answer, because now maybe one of them is incorrect, maybe 2 of them are incorrect, but it's unlikely that everything is wrong together. So I would want a solution which looks like this and not like this. So quick comments is like, again, this might look simple, but this has a name, like this is called a perceptron or logistic regression. It's also called a densely connected layer or a densely connected network because like every single input is connected to every single output. Like there is a connection between everything. And you could also call this like shallow learning as opposed to deep learning because we only have one layer between the input and the output. Like there is just input, a filter, output. So this would be what makes it shallow. And the other thing is like machine learning is really all about like give me input, give me output, and I'm just trying to figure out weights which will make the system work. One way you could also look at this is like in the end, all we did was we said like we have like two components which are two filters of same shape, like 8 by 8, 64, and we're essentially building something which is a circuit board. I'm going to give you input, I'm wiring all the circuit, and I'm telling the circuit, like, this is what I want you to predict, this is what the program should be doing, and then I'm going to feed it with examples and more examples, and what I want is I want the circuit board to learn all by itself, like, given the examples you gave me, I'm going to create a board which does exactly the task you wanted to do. So you could see this as like building a circuit. Elaborating a bit on the idea of the circuit is like so far all I looked at was filters which were, I have an input which is 8 by 8. I'm using a filter which is 8 by 8. This is one thing I can do, but I could also do something a bit different. For instance, I could look at the image of a 2 here, and I could say really a 2, which is like 8 by 8, could be broken down into a 4 by 4 section and a 4 by 4 section, like 4 different areas here. And so the type of system I could build now is like instead of having a single filter, I could say I'm going to use 4 filters. I'm going to have one filter here which corresponds to the subsection here, which is going to detect in this image, do I find this shape? And I could do the same with another filter which is going to look for this shape in this image and so on and so forth. And so that situation, what I would get is like a filter which tells me, yes, I found this shape or no. So that would give me 0 or 1 as an output. Yes, I found this shape, yes or no, 0 or 1 output. So I would get like 4 outputs. And essentially, if I find this shape and this shape and this shape and this shape, then I know for sure it's a 2. So the idea here is like instead of looking at one big shape, which is a 2, I'm trying to recognize much smaller shapes. Part of the point is like some of this shape could be actually reusable to recognize a 3 or a 4 or other things. Like if I take the shape on the top here, that would belong to a 3. So now the pattern to recognize a 3 would be if you find this and you do not find this, this is possibly a 3. So you could start to combine all these filters to get, and combine them together to get actually the answer you want by recognizing smaller patterns. And one way to represent this in maybe a more abstract way would be what I'm doing here is I'm saying I want really 4 filters or 4 sensors here which I laid out. Each of them is going to give me one answer which is yes or no, I found this thing. And then I'm going to plug the output of everything from this side here, and I'm going to plug it into another array of sensors which is going to detect combinations of patterns I found before. And I could keep going and going and going, and so the type of model I'm building here, I could describe as I'm going to put, say, 6 filters of a certain shape as the first layer. I'm going to plug them all into, in that case, like 4 filters of a certain shape, and I'm going to plug them all into more filters and more filters. So what I'm doing here is I'm composing what people call layers. So here I have like 3 layers which have a certain shape, and I'm all connecting them together. And the role of each layer is to detect certain types of patterns and then combine them into other patterns and other patterns until you get the answer you want. So this is where you go from a shallow learning model to a deep learning model, because now instead of going from one input, filter, output, I have like filters to filters to filters, and these are the layers in your model which makes it deep. So recap is like what we're trying to build here. A deep learning model is a model which is composed of stacks of layers. Each layer is recomposed of filters or sensors which have a certain shape. And the way you're going to use this is by feeding it examples until the filters are configured in a way where the answer you get is actually what you wanted to see. So this is, I promised, like a shallow exposition to deep learning. So this is where I'm going to leave it, but I hope it gives you a bit of a sense for how a deep learning model might work. Now what I want to do is I want to go into CNTK and talk a bit about how the library looks. So first is like, what is CNTK? So CNTK is one of these wonderful acronyms for Microsoft. It's really a beautiful name. So CNTK stands for Cognitive Toolkit. The project is open source. So if you go to GitHub at GitHub Microsoft CNTK, all of it is there. the whole core, and they take contributions, and so yeah, it's open source. One of the specific things which makes CNTK interesting is that the library allows you to run your models on a CPU, so you can run it locally on your machine. You can also run it on a GPU on your machine, and you can also run it on a farm of GPUs if you really need that type of power. So this is kind of nice. The last bullet point is saying that this is similar to TensorFlow, so you can, they are pretty much, I would say, equivalent. One of the advantages of CNTK is this piece about like distributed GPUs. It's supposed to be better or like very strong at that aspect and better than TensorFlow at that. The other reason which made CNTK interesting to me is, so Microsoft has a bit of a history of like shipping a library, and they tell you this is really what you should be using, and it's awesome, and you should use it, and then 6 months later, it's like the library is canned, and now like, hello Silverlight, and so now you're in the middle of nowhere, you don't know what to do next. So one thing which made me interested in CNTK is like CNTK is actually what Microsoft uses internally for the deep learning stuff. So they use it for Skype, they use it for Bing, they use it for lots of things. And so it's good. It's a good thing for me because, like, one, I'm pretty much sure that in 5 years, like, CNTK is still going to be around. So that's good. And the second one is like if it works at scale for the type of data sets which they use at Bing, it's probably going to be good enough for my tiny data set. So like, I'm reasonably confident that this is a good library which will scale up to my needs. Technically, CNTK is built on a C++ core, and on that core, you have a bunch of languages which are supported. So you can use Python, you can use something called BrainScript, which is like a kind of a custom language, scripting language built for this. You can use .NET, so meaning you can use C#, you can use F#. You could even use C++ if you wanted to build your models in C++, and if you're a masochist. So CNTK does all these things. So now that I described what CNTK is like, what does CNTK do? So CNTK does a couple of things for you. The first thing beforehand is like I described building a model as essentially layers connecting input to output. So CNTK allows you to specify, I have that type of input, I have that type of output, this is how I want to connect them. So specify that. The second one is like if I want to feed examples for the model to learn, I need to read data from somewhere. So it provides you with a bunch of readers which allow you to read. You need to learn weights which work for your model, so it's going to provide you with a way to learn the weights. And finally, learning a model and not be able to use it would not be very interesting, so you can also train a model, save it, and then reopen it and use it in your own code, whichever way you find fit. In that frame, the core components you will see in the library are the following. So it's the most basic component in the library is what's called an ND shape or a tensor. I'm going to talk a bit more about what a tensor is in a second because it sounds intimidating. It's not that complicated. The second piece, which is at the core of the library, is the idea of a function. So in the end, when you build a model which connects input to output, what you're going to get is a function. And the function takes different types of parameters. They can be input variables, parameters, or constants. I'm also going to talk about why that is the case. And you get also a class which is called a trainer. And so a trainer is simply something where you give it a model, you give it a reader, and it's going to learn. And finally, you get readers, and specifically mini-batch readers. So one of the reasons reading is interesting in this context is that if you have a small data set which fits in memory, it's fine, you can read it all and it's easy. But if you had a very large data set, maybe you cannot read everything in memory, and so you want to be able to read through your data set in maybe a slightly random fashion, and so what you get is like readers which allow you to read by blocks of 100 and kind of go randomly across your data set. So these are like mini-batch readers. So I said like the core component was a tensor or ND shape. So tensors is one of these things which sound very intimidating. Initially, I didn't quite know what a tensor was. And after a while, it dawned on me that a tensor is simply an array. And the reason it's called a tensor is that it's an array which can take n dimensions. That's why it's called an ND shape as an n-dimensional array. So the reason they use that's also why TensorFlow is called a TensorFlow, is like it also uses tensors. So the reason this is useful is because you can represent a lot of things with this. For instance, like if I consider the idea of an image is really a 2D array where I have my pixels, so that would be like a 2D tensor. If you had an image with maybe colors, it's like you could represent it as a 3D tensor because you would have maybe 8 by 8, and the first layer would be a red, the second layer would be green, and the third layer would be red, green, and blue. If you had a movie, you could represent this. So a movie would be a sequence of images. So now you could represent this with a 4-dimensional tensor, because you would have 8 by 8 images with 3 colors, and the frames would be another dimension to the array. And I can't think of an example beyond 4 dimensions, but maybe there are some. But so that allows you to represent a lot of things. The other thing which is useful about it is that it makes composition very easy, because if your functions all take as an input a tensor, an output a tensor, then you can start to plug very easily things together. So this is why tensor are at the core of the library. And so, for instance, if I go back to the example of I'm trying to recognize ones or twos, the type of model I would build is something like this. My input variable would be a 2D tensor, and the dimension would be 8 and 8. So this is saying like my tensor, my array has 2 dimensions, and I expect like 8 by 8 pixels. Similarly, my weights would be a 2D tensor, 8 by 8, and the output should be either a 0 or a 1, and so that would be a 1-dimensional tensor with only one element. So that gives me like a way to represent the structure of my data. I could also represent this in code, and I could say like the way this model works is really saying like the output of my model is like 2 operations. The first one is I'm getting an array of 2 8 by 8 pixels, and I'm going to have 8 by 8 weights. And so the output of my model will be take the first pixel here, multiply the value by this, plus this, multiply by this, and so on and so forth. And the output of this, I would feed into a second function, which would say if the output you got out of the first operation is greater than a certain threshold, then predict it's a 1, and otherwise predict it's a 0 because it's not a 1. That would work as well, and in the end, when you train the model, this is what you will get. It's like a function which does exactly this. So I could write this as a function like in F#. It doesn't really matter what language this is. The function I would get in the end is something like if you give me inputs which are a 2D array of floats, weights which are a 2D array of floats, and a threshold which is a 2D array of floats, I would compute their product, I would compute the sum, and if it's greater than the threshold, I would give you a 1 or a 0. So the reason I wrote this that way is while this is what you want as an end product, this will not be sufficient for the library to work. Because as part of the training process, I described it as like tweaking the weights so that you can get the output you want. So if I just had like all these inputs as just arguments, the library would have no idea what are the weights, what is it that I can actually change, and what are the inputs I'm not allowed to change. So this is where the idea of, I mentioned earlier that we have like multiple types of inputs. And the first type of input I have is like an input variable. So this is something you will get. You cannot change it. If I give you an image, this is the image. You cannot tweak it. And the parameters are what I called the weights earlier. So these are the things the algorithm is actually allowed to tweak. So even though in the end, like the function is going to be a function of just floats or tensors, during the training process, you need to be able to distinguish what you can change. This is the parameters, and what you get as an input, which is the input variable. And so in this case, like a function is going to be a function of input variables and parameters. So now I talked a lot. I'm going to move a bit into code, and I talked a bit about the idea of distinguishing between a 1 and a 2. So I'm going to actually build exactly that using CNTK. And first, I'm going to do it using CNTK out of the box without the type of thing I've been doing, so to show you a bit how it works, and also the pain points I found by using the library. So I'm going to do a slight change from what I presented. Like when I described how I would build this, I said initially that I would use like 2 filters, one for the 1s and one for the 2s. What I'm going to do is something slightly different, and what I'm going to say is like I'm really going to use a single filter, and the single filter is going to have like strong positive weights for the yellow section is like the weights which correspond to the 1. So I put them like on the filter here, and the blue ones are going to be very negative weights, or the weights which correspond to 2. So my point here is like if I have like strong positive weights for the 1, it's going to give me a very strong signal which is sees a 1. When I'm getting if I get very negative weights for the 2, when it sees a 2, it's going to give me a very negative signal, and when it sees something which is neither a 1 nor a 2, or it doesn't know, I'm going to get an output which is 0. I don't know what it is. So it's going to give me high positive signal for 1, high negative signal for 2, and 0 when I don't know. Yeah, so that's kind of what I'm going to build now. So let's go now into VS Code. And so So the part of the goal I had also with working with this was that I wanted to be able to work with VS Code because I want to be able to work from a scripting environment. It's like Visual Studio is awesome, but it's kind of heavyweight for this type of work. So I want this to work with VS Code. I created a NuGet package, so the version is like 0.1.3, so that gives you a bit of a sense for it's not entirely mature, use it at your own risk, but like it works. And once you have the NuGet package, you don't need to install anything, like nothing to install on the machine, just put the package and it will work. At least in theory. It works on my machine, so it will work on yours, obviously. So I'm going to load my library here. Just fine. I'm going to load all that stuff. So the first thing is like, if I want to recognize 1 from 2s, I need images to learn from. So what I did is I created a big data set, like with a huge sample of like 64 images. And the 64 images like I created by hand. So the way I created them is the following. Is like the images I'm looking at is exactly what I described. They are like 8 by 8 images of either 1 or 0. So it's either 0 or 1 pixel by pixel. And what I did is I created 32 versions of this for the 1 and 32 versions of this for the 2. And to make it a bit more interesting is like I added a bit of noise. So I started flipping some of the bits to 0 or 1 randomly. So as a result, my data set looks like this. My first 32 images are like 1s, so this is the label. Label is a 1 because it's a 1, and here you have pixels, which is going to be 8 bits, then 8 bits, then 8 bits. And if you look at this, like all these are pretty similar, except that in some cases here I have like some subtle differences between the images, which are noise I just added to it to make it more fun. And the second part of the data, so I have 32 1s, and then I have 32 2s. And because I'm not very smart, is like what I did is like the label now is 0 because it's not a 1. So it's a bit confusing. It's really saying like when it's a 2, the label is going to be 0, and when it's a 1, the label is going to be a 1. In hindsight, I should probably have picked between 0 and 1. That would have made things easier to follow, but hindsight 2020, so that was a bit of a mistake. Anyway, so now I have data. And what I want is like I want to take this data set and I want to learn the weights which are going to make my model work and recognize an image of a 1 from an image of a 2. So I'm going to go here. And so what I need is like, I mentioned that I'm going to have like inputs and weights. So the first thing is like I'm going to create a set of inputs. These inputs are going to be an input variable because this is the image I'm getting. And this image is going to be, so I flattened it out, but like essentially I'm saying that you're going to get 64 pixels. This is the input you have. And the data type is going to be floats. The weights are going to be a shape which is similar, but now is like this is not going to be an input variable, this is going to be a parameter, because this is the type of thing the model should be modified to get the correct answer. So let's do that. I'm going to also add a constant, and now I can build a model. So my model is going to say like, take the weights, which is a parameter, take the input, which is an input variable, and multiply this. And once you multiply this, like I'm going to add it to a constant variable, and for technical reasons which I don't want to go into, I'm going to push it into something called a sigmoid. But like essentially, this is what I described before. So multiply the weights by the input, and give me that as an output. You might have noticed here that I'm using here something which is CNTK lib. So this is one thing you get out of the library, CNTK lib dot. And what this gives you is a bunch of operations. So you can see things like apps, cosine, like equal, augment, so all of this. So what this gives you is like the ability, all of these are operations which work on tensors. So what you can do now is you can take tensors, you can add them, multiply them, all of this is built for you, and you can then build arbitrary complicated mathematical expressions using this. The thing which is awesome about this is one, it will work on any tensor, and two, that expression will be runnable on a CPU, on a GPU, on a form of GPUs. So in other words, it's like it's a bit annoying maybe to have to write like a CNTK lib multiply instead of multiplying things. But what I get for this is like once I have specified my model, I can run it on anything I want. So that's cool. And also model is a function, so if I look now at my function here, model dot, I will see that I get things out of it. I can retrieve or I can inspect the model. I can ask what are the inputs, what are the outputs, what are the parameters, so I can start to inspect how the model itself is composed if I want to know what the model is doing. So now I created my model. The next step is like first I need to tell it what I want to learn. So this is going to be an input variable, which is like I want you to learn between a 1 or a 2. That's going to be now a shape of dimension 1, like a tensor of dimension 1. And here comes the part where, so far it's not too bad, but here comes the part where it's a bit ugly. So as part of the point, I left it. This is what you would get if you use the library out of the box. So I'm going to tell it, if I want the model to learn something, I need to tell it like what is good, what is bad. So this will be the loss function, which is going to measure how close or how far are you from the answer you want. So that would be, in that case, squared error. Like this is saying, like, look at the output of the model, look at the label you're trying to predict, and the further apart these two things are, the worse it is. So you're trying to make this as small as possible. So we're going to do that. And then a long series of annoying settings is coming up. Now I'm going to tell it, like, this is how I want you to learn. I want you to learn parameters using this particular algorithm. I'm going to create a trainer, which is going to try to train that model using that loss function and using that particular strategy. And now I'm going to set it to read the data. So here, I'm going to set up a reader, and that reader is going to look for something called pixels, which maps what I had in my file here, which was pixels. And I'm going to have a reader for something called labels, which is also mapping the other field I had in my data set. So I'm saying, like, if you look at the data set, you're going to find these things. Pixels is going to be 8 by 8, and label is going to be one value. And now is like I'm going to create my mini batch source, which is going to say, like, take this, look at this file called images, use the reader I have, and that should be sufficient to read. And now even more gory setup comes up. So I'm going to set up the stream. I'm going to set up the device, so I want you to learn on a CPU. I'm going to set up the mini batch data. I'm going to tell it, like, this is what you're going to learn. So this is a bit of a painful setup, and this kind of the part of the point I want to make. Is like the beauty is like this works. The annoying part is like the setup is quite unpleasant out of the box. Now that I'm set up, is like all I have to do is like I want to read the data, so let me run it. The trainer I just created is now going to look at the data set I gave it, read the batches, and I'm going to read like 1,000 times, and every time I'm going to try to adjust the weights and adjust the weights and adjust the weights until it gets to the answer I want. So on the output here, you see popping up is like I'm going to go all the way back up. And so it did like 1,000 passes, and what it starts with is initially the loss function, which is like how good my model is pretty high. It's like 0.38, goes down a bit, and as we go, you can see that as the model is learning weights and passing through the data over and over and over again, it's getting better and better and better at making predictions. So this is now the model has learned something. And let's look a bit. What I want to do now is like I want to show you the weights the model learned. So let's do that. So I'm going to extract out the weights for my model, and I'm going to visualize them, and I'm going to go very old school. So I created like a WinForms display because this is the future. I believe in WinForms. And so this is like an 8 by 8 display of the weights. And if you recall what I predicted is like I would expect weights first, like I would expect like 64 weights. And what I say is like if it learned the way I thought it would, I would see yellow weights. So yellow indicates like very strongly positive weights. Dark, close to black is like things where like it's 0, it doesn't quite know what it is. And when you see a strong blue shape, strong blue color, it's like very strongly negative weights. And this is pretty much exactly what I predicted the model should do. What I see here is that I see a shape in yellow, which is pretty much the outline of the one I described. Out there in blue, I see the outline of the two I predicted I would see. I see that mostly here the bar is like dark because I said like the model shouldn't learn anything out of this. The pixel in the middle is also dark. There are some mistakes, like for some reason it thinks that this might be a bit important, that this is also not quite dark. So this is in all likelihood due to the fact that it introduced some noise to the data. But overall the shape of the weights I'm getting here is kind of what I predicted. Of course, it's not proving that I'm right and that I'm correct, but I hope at least it shows you that I'm not completely full of it, and like what I told you is reasonably close to the truth. So now I'm going to go back to my slides for a minute. And yeah, the point was like what I predicted is I predicted that I would get weights which look like this if the world was perfect. The world is not entirely perfect, but what I got is this, which is reasonably close. So I'm happy. I'm reasonably convinced that things are working the way I want. So now I want to move to the third part I wanted to touch on, which is like how can you make composing models in CNTK a bit nicer? So in case there was any doubt, is like I complained quite a bit like during the setup of the model because like a lot of it was quite unpleasant. Like there was a lot of code to just reset up things. So in other words, like out of the box, the .NET API is extremely low level. Like it gives you the breaks you want, but it's like here are the breaks and like now build a house. It's like I would like something a bit higher level, which allows me to compose models together. What I described was a deep learning model is typically something where you stack together high-level components, and so I would like to be in that world and not in the world of like multiplying tensors by hand. And the inspiration I took was also, this is typically what people do on TensorFlow and other places. There is a library called Keras in the Python world which allows you to do that type of thing, and so I took that a bit as an inspiration for what I wanted from CNTK. So I couldn't do everything because like, this is a big project. So if I look in general at deep learning models, they can take a wide range of shapes. Like the most general model you could do could potentially look like this. Like this is essentially an arbitrary complex expression where I have like multiple inputs which could go to multiple layers. You could have forks, you could have joins. So this is a pretty complicated structure to model. So this is hard. I don't like things which are hard, so I thought let's take the simpler problem. And so the simpler problem is the one which is on the right here. And so the thing on the right here is really saying, like, I'm going to have a single input, and what I'm going to do is I'm going to take that input, pass it into one layer, and take that layer, feed it into the next layer, and into the next layer, until I get like a single output. So this is what people call a sequential model, because it's just like input, sequence, 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 output. Much simpler, no forks, no joins, easier to tackle. And it's not only that it's simple, but it also fits with a lot of models. For instance, the case I gave you, which is here is an image, give me the output, fits pretty well with that. So you can do a lot of things with this. So I thought, let's go with the 80% case. The other thing which got me intrigued was if you come from functional, specifically from M#, this is very close to the pipeline style of operations you would typically build in F#. And so what I'm looking for is something where I could say, like, I want a model, and that model is going to take an input, apply a layer, which is a transformation, transform by applying layer 2, transform by layer 3, up to the moment you have an output. So this is kind of what I was gunning for. So the case I'm going to show you now is I'm going to look at a data set which is a super classic in machine learning called the MNIST dataset. So this is a data set of numbers which have been written by humans. For the anecdotes, like this is actually coming from people writing zip codes on, at the post office. So if you take a letter, you have like 5 numbers, they're nicely in little boxes, so people just took this, scanned this, and there is a huge data set of numbers where you have images, and you know what the image is. And so my goal here is going to recognize numbers between 0 and 9, so take an image and tell me what number is this. And to do this, I'm going to use something which is called a convolutional network. So I'm not going to go into deep detail on what a convolutional network is. But the way this works is like it's using essentially 3 components. The first component is called the convolution. And so what a convolution does is like it's pretty much what I described earlier with filters. A convolution of size 4 by 4 is going to be a filter which recognizes a pattern of 4 by 4. And it's going to scan the image and try to figure out, did I see it here, did I see it here, did I see it here? So the convolution is trying to pick up like small patterns into an image. The activation is what I described earlier. Like activation is really saying like, if the signal is strong enough, give me a 1, otherwise don't give me a 1. Or like decide when the signal is strong enough. And the last one is called the pooling layer. And so pooling layer is normally used to simplify a bit the data you have. Essentially, it's saying, like, if you found this pattern in this broad area, I don't quite care where, just tell me you found it in this big area. So it's kind of simplifying a bit. You don't have to carry that much data around. And so, yeah, the input looks like this. I have images which are 28 by 28. It's a bit more, so that's more data than before. They are also going to be more complicated because now I don't have just 1 and 2. I have like every possible number. And it's also a bit more complicated because the input is not going to be just 0 and 1. It goes from 0 to 255 because they are grayscale images. So without further ado, let's go into a deep learning model. And so I'm going to show you like how that would look using like my current work. So let me first kill this. And now let me go into this guy here. So same setup in the beginning. I'm going to load my library. I'm going to load my package. This is fine. And I'm going to go here. So now, instead of having just one output, I have 10 possible outputs. So I'm going to still create an input variable. In that case, my input variable is going to be a shape which is 28 by 28. For technical reasons, I don't want to talk about also, I'm also saying like it has an extra dimension of 1. Ignore it, like it's not very important. So input is like 28 by 28. The labels now, instead of being a single number, is going to be tensor, which is going to be of 1 dimension, which is going to be 10. So I could get 1 of 10 possible outputs. And I should also start it by showing maybe the data. So I prepared the data for CNTK. So here what I have is like instead of like 64 tiny images, I have now 5,000 of them. So it's a slightly bigger data set. I still have labels like the thing I'm trying to predict. But now the labels, because I'm trying to predict 10 numbers, so this is what's called like one hot encoded. So what I see here is like I have 10 numbers which can be 0 and 1, and the one which is set to 1 is indicating which of the possible 10 answer is active. So in this case, it's saying me this is not a 0, this is a 1. This is a 0, this is not a 1. And here, for instance, like 0, 1, 2, 3, so the third one is active. So this is telling me that this particular image is a 3. And what I have afterwards is I have 28 by 28 pixels, which are the description of the image. So a lot of zeros, but afterwards you can see that they are pixels. So this is essentially the same type of input I had before, just more of it and a bit more complicated. So I'm reading it this way here, saying now input is 28 by 28, output is going to be 10 values, and now what I want is I want to compose my model and stack layers which are going to be convolutional layers. So first is like I created a couple of types. So here I have something which is called a convolution, and I'm going to use filters of size 3 by 3. So the kernel is essentially describing like how big do you want your filter to be. So here my convolution is going to be 3 by 3. Look for 3 by 3 patterns into the image. Let's do that. The pooling layer is going to be quite similar, but it's saying like when you aggregate things, it's like look at areas of 3 by 3 and reduce them into one thing. Like if you find that pattern in any of these 9 pixels, I don't care, like just tell me it was there. And now all I have to do is to create a network, which is going to be a computation. So this is what I created. And all I do here is I'm going to stack layers together. So I'm going to say like my computation, first take all the input and rescale them because I don't like things to be between 0 and 255. So put everything from 0 to 255 to 0 to 1. It's going to be easier for computation. Then I'm going to add a layer. That layer is going to be a convolution. And I want like 4 filters of that type. And then I'm going to stack it with an activation, which is called a ReLU, like a rectified linear unit. So activate this based on this, and then use a pooling layer. And then I want more layers because it's a deep learning thing, so I'm going to put another layer of convolution. Now I want you to use 8 filters. And now I'm going to stack it again in an activation, and I'm going to put it in pooling, and I'm going to finally connect it into a dense layer. And so this is neat because all I had to say was like, take this layer, stack it, stack it, stack it, stack it, and my model is now completely done. Much more elegant than before. Now I can say like create a specification for my model. So this is the input I specified before, output I specified before. The model is what I just created. The loss is, I'm going to give it here. And now all I need to do is to connect it to the data. So here I'm going to say like here is where you're going to look for a feature called features, for labels called labels. And I want you to read by batch of 64. I want you to do it 50 times. I want you to run on the CPU. And I won't talk about this because that would bring me too far down the rabbit hole. Now I can set my data source. It's a text format source. Here is the file. Here is the features. And I should be able now to train my model. So let's do that. Here is my trainer. And now, here we go. So now let's do it. So now this is going to be a bit more work than before because I'm looking at a slightly bigger data set, like more features, more weights. Like now instead of like 64 weights, I'm looking for a bunch of layers. Each of them have all their weights, and it's like 50 iterations over the data set. So I'm looking like 50 times 50 times data set of 5,000 broken down into batches of 64, so a bit more work. But if you look at what's happening here, it's like same type of pattern, and the loss is progressively going down and down and down. So it's like it's confidence inducing, like it's telling me that the model is probably is getting slightly better. It's actually getting pretty good now at predicting the type of output I want. So I'm going to let it work a bit more. And now we have a model. So the model is trained, and what I can do is I can say, great, now you have a model. How about you save it? So like my model is going to be saved as a file. That file is going to be right here. So this is the thing I call the convolution model. And if I open it, so the marketplace apparently has an extension which could help me with this, but I don't want to look at the extension. So this is like how the model is saved. So it's like, I don't know the exact format, but if you blink a bit, you can see that this file is containing like all the model I specified. It's containing all the weights I trained, so everything is in here. And the beauty here is like this is saved, so now it's like I can reopen it in Python, I can reopen it in C#, I can reopen it anywhere. Like CNTK knows how to read this, recreate a function which I can now use to make predictions. So this is like the whole truth about the thing the model learned. So the way I could, for instance, use it is I could say, fine, I'm going to reopen that, I'm going to take that model. And now what I would like to do is I would like to take the model I just trained and I want to run it on a set of images to see how good does it do. So I put on the side like 500 images, which is going to be my validation set. And I'm going to now take that model, reopen it, and I'm going to check like how good does this do at predicting images. What did I do? I probably forgot to run this. Here we go. And so so here are like a couple of numbers. So this is not particularly exciting, but in this case, I'm looking at 500 images, and the model is making overall across 500 images, it's making like 9 errors. So this is pretty decent. Like it's something like what is that's like 2% error, something like that. So it's pretty okay, right? Like 98% correct. Numbers are cool, but like maybe this is not that exciting. So what I'm going to do as well is I'm going to just visualize a bit. I'm going to take some of the images and just display like how does the prediction look, or like what did the model do. So here are a couple of images from the data set. So first you can see that they are like human written, like they're not perfect, they are kind of messy. And here you can see that it was a 3. The model tells me it's a 3, so that's good. A 1, so that was not too difficult. A 1, so that's a bit harder maybe. A 5, like this is starting to be a bit harder, and the model is still getting everything right here. Again, like a 7, like not completely trivial. So far the model is like batting 100%. This one is like, I don't even know if I would guess myself that this is a 7, but like, the model called it right. So it's like, sure enough, like, it's maybe better than me. Even things like these ones, like this one is kind of cool too. You can see that it picked up that it was a 9, even though there is a big smudge on the number. So like so far the model is doing pretty well. So again, like it's not proving anything, but you can see that fairly easily I was able to set up a model, give it a data set, and like the model which comes out of it is actually doing a pretty good job at predicting data, which, see, look at this. Like this is supposed to be a 2, and the model is actually calling this as a 2. So it works, is my conclusion here. So let me close this. And let me go back to my slides for a minute. Yeah, so conclusion is like what I hope I show you here is like again like the version number of the package is like 0.1.3, so it's not finished, it's not perfect, but you saw hopefully you saw that it's usable. It's like I used it here, like it's not horrible, it doesn't do everything, but it works. The part which is decent is like building sequential models, specifically convolution. I have that like mostly working. The next steps for me are like I want to work more on sequential and add more layers, in particular things like recurrent networks and all like more types of layers, but like that part is like underway. The part which is not done and a bit more complicated is like non-sequential models, so I'm still working on that part. If you are interested in it, like the NuGet package and the repository, like look for cntk.f#. It's all there, it's open source, so look at it, criticize it, send me pull requests, tell me what you want. I also wanted to give hats off to a guy called Avi Avni, who has been sending me contributions, which have been quite helpful. He's awesome, so hats off. The last thing I wanted to mention also on deep learning with .NET is like there is another library which exists, which is called the TensorFlow shop. One of the reasons I went to CNTK was it was the first one which had a .NET API. As it turns out, it's like TensorFlow Shop is a project which aims at putting a .NET API or TensorFlow. It's out there. It's one of the main contributors is Miguel de Icaza, so I'm suspecting that it's probably very good. It just happened after I started working on CNTK, so look at it. I haven't tried it myself, but I wanted to mention it out there because it's another interesting piece of work. And this is what I had. So I guess is like what I have to say. Like, thank you. I hope you got something out of it. You can find me on Twitter here. Again, like if you want to help me with the code or you're interested in contributing, like find the repository in CNTK shop. And if you want also to find me, like I encourage you to join the fsharp.org, the F-Sharp Foundation, where there is a Slack channel where I'm hanging all the time to talk about machine learning and data science, so that's a great way to find me. So thank you very much. And I think I even have a couple of minutes for questions, so if people have questions, I will gladly take them. And if people do not have questions because it's the end of a long day, I will gladly not take questions and let everybody enjoy the party. So questions, going once, going twice, going thrice. Yep.
What is pooling? That's
So,
a term I haven't seen.
so the question is, what is pooling? So what I described is like the first thing I described was the convolution. And so the convolution is saying, if you find this 3x3 pattern on the image somewhere, give me a 1 or give me a 0. Specifically, what the convolution does, it doesn't only tell you, I found this in the image, it tells you where it finds it. So it's scanning across. And now what you imagine if I did this is I could see like 0, 0, 0, 1, I found it here, 0, 0, 0. In the end, is like I don't entirely care where you found it. It's like it's enough for me to know essentially like it's in the upper right corner or upper left corner. And so pooling is going to say, if you find something active in this 3x3 area, just tell me it was active. So like instead of like 3x3 pixels, it's going to tell me either 1 or 0 and not like a whole zone in the picture. So it simplifies or it summarizes the information. Does this answer your question?
Yes.
Cool. Yes?
How do you decide the layers?
This is, how do you decide the layers? Well, you go out with your goat under the full moon, you sacrifice it and you hope for the best. No, part of it is, so it's a good question, and that's, I should probably have talked about this, so thank you for asking it. That's one of the reasons I wanted to have a model where it's easy to compose and change the layers, because like the short answer is like you don't know until you try it. So if you work on image recognition, is like people have looked at that problem quite a bit, and so you have a good idea of like what type of thing might work and what type of thing won't. But you will still have to tune it, and so you might have to add like more layers, less layers, like more filters, less filters per layer. And so this is where like having a model where you can compose and change the model easily is very important. Like the code I showed you, if I decided to maybe use 16 filters instead of 4, I would just have to change one number and I could just run it. If I wanted to add one layer, I would just like add it to it and I could run it. So, so you don't know what the right structure is, and that's actually part of the craft. And it's where you're going to spend probably quite a bit of time if you do a deep network, is just figure out what type of structure might work. So there is I wish I had an answer which is this is exactly what you should do, but like what you should do is like try it out until you find something which works, hopefully. More questions? Last call. Good, then thank you very much, and like enjoy the party tonight, and thank you for coming.